So one of you came by office hours and mentioned on problem set 4, there's a typo. It wasn't terrible, but it did, you guys, all of you should have been bothered by this. It makes me worried that you're not looking at it. And that was the anvil question. And the anvil question was you heat an anvil. I can't really draw an anvil, but actually it's not so bad, right? I surprised myself what I can do. So you heat an anvil and you calculate the change in entropy. And I mentioned this in class, but it bears repeating. Oh, this pen is dying. That the change in entropy, it's not, I ballyhooed quite a bit about how the change in entropy is always CV ln TF over TI plus NR ln VF over VI. What I did mention just once though, so it's fair that this would have been confusing. Those are magic cylinder questions, but not everything is a magic cylinder question. Like an anvil is not in a cylinder. So if you want to look at this as a state function which takes different legs, path 1 plus path 2, you can't say that it was at constant volume. That's impossible because it's simply not encased in the cylinder. Nor is the anvil cast in a die. In other words, you can't heat it and not have its volume change. So that means it's at constant pressure. Now, on the homework answer key, I had accidentally mixed up CP and CV, and that was the typo. But it was a good idea, a good opportunity to point out that not everything is a magic cylinder question, and so this is a little bit different than the paradigm I had talked about before, where everything is always CV ln TF over TI. Again, that's true only if you have something captured in the cylinder. Now, what I'm going to do though is I'm not going to have these kinds of questions on the exam. They'll be magic cylinder questions because that's what we focused on. So I did want to point that out, and I fixed the answer key. So when you folks hopefully are looking at those, remember that I wrote all this. So the same person who wrote the homework wrote the exam. So look at those answer keys. Also reviewing what we covered last time, and I'm going to do this in a slightly different way than I normally do. Unfortunately, I have another pen. Okay, we covered the Gibbs-Helmholtz equation, in which comes about because our usual does it go up or does it go down gets tricky with Gibbs energy and temperature. dg dt at we did this at constant p because p is the other natural variable. So that's one I would like to hold constant. I can hold anything constant, but I'll hold p constant. And remember, minus t squared. So it's actually equal to minus entropy. And entropy is a nightmare, not delta. We've covered all the equations for entropy, a change in entropy, and I even showed you what entropy actually is, KLN, number of microstates. So that's really difficult to work with. So instead we cast it into this form, but we also had to divide. We can't do dg dt directly. Again, I'm just reviewing. We had to do g over t. And we run into change of g over t like an unbelievably large amount of time in the third part of this class, so that's useful. It was also doable, so that was also quite good. And I want to point out, so this is where I'm going to do review a little differently because we're getting into actual chemical reactions. And by the way, we're always going to do gas phase reactions. Be really careful when you're doing Hess's law, G products minus G reactants. Be very careful of phase. That's something I'm not trying to trick you, but if you're doing Hess's law calculations and you look at data tables, water solid, water liquid, water gas are all present. Make sure you get the right one. Anyway, so you can imagine that delta G of this reaction, now let's do some symbology. Little r right here means change in G, you know that. R means reaction, would be the G content of B minus the G content of A. Now if you wanted to change the temperature, you might know these numbers at, say, room temperature, but if you wanted to do a higher temperature, you would use the Gibbs-Helmholtz equation, you would use H. So what you would do is you would calculate the change in the G for species B, using the enthalpy of species B, the absolute enthalpy, and then you would do the same for A, using the same equation, and then you could calculate delta G at a different temperature. Okay, not terribly hard. Again, it's like advanced high school hard. You just have to use your calculator, which is a bit of a nightmare. Now, you could also do this. And it's not trivial just to throw in this delta, but what you do is mechanically you get delta G just like you did here. You know, like Hess's, high school. How you did in high school, Hess's law calculation from high school. You would get delta H the same way. So you can do it all at once. So if you need to know delta H, I didn't like that minus sign, by the way. So if you want to get delta G at a higher temperature, you could either do each species individually, or you could just do the change of the reaction, the change in delta G. What's the new delta G at a different temperature? And you just use the delta H of the reaction. It's, in terms of your calculations, it's the exact same thing. It's just like a gazillion times easier to keep track of if you do it this way. And you're going to be doing that shortly. I'm actually kind of previewing here. So anyway, I just wanted to point that out. It's also kind of relevant to what we're doing in class. And of course, the way you would know G of each and every one of these species is, so G of B, of course, is U, oops, that's supposed to be a U minus TS plus PV. I wrote this out of order, by the way, but that's H minus TS. So you can imagine you get that from the equal partition theorem, pressure volume. Again, we're going to be doing gas phase reactions, and I'll talk only a little bit about how you do non-gas phase reactions, but I'm not going to say too much about it, unfortunately, because I don't think we really know as much as we'd like. In all honesty, I know reactions work when I do them and I get products. That's unfortunately still largely the case, was back then it is now. Okay, anyway, gas phase reaction. So I know U from equal partition theorem, for B. Of course, it's a gas, so it's in a certain volume, and I have a pressure gauge. Temperature, I know the temperature because I have a thermometer. Entropy. Okay, so now I need to know the entropy, and that's not delta S, it's S. Now we're not going to be doing KLN number of microstates, because again, when you're doing that on something real, not some silly chess piece on a chessboard, which is not real, but, illustrative. That's why I ask you those questions. It looks like you need to know entropy, right? So I'm going to tell you how we calculate absolute entropy experimentally, not with KLN number of microstates, which again, you have to get a graduate degree to even begin to be able to do that. It's more of a way of thinking than a way of necessarily doing, Hess's law calculation. Okay, to do that, entropy is so terribly important. I'm just reminding myself, by the way, maybe don't write this down, but I just want to make sure what I said before was correct. Entropy is, so dG dt at constant P is minus entropy. I'm just reminding myself. So, again, we had to practically do this, we had to do Hess's law. But I do see that I've run into a lot of things just in this 10 minutes I've been talking where I really need to know what the entropy is. And if I think of it as a grad school KLNW, that's really not going to work so well because I'm not sure anyway. All right, so how do you calculate and tabulate entropy? How do you do that? And that is actually the third law. The third law, in some ways, simply says entropy exists, which is pretty useful because the second law says that total entropy always increases. That's why everything that's ever happened, that's why my leg is hurting, because entropy's increased. I don't quite know what that means or how that came about, but everything that's ever happened is because of the second law. The third law gives entropy a face, an absolute face. It gives us a way to calculate it. Everything, a lot of things we've been doing have been relative. Remember that I said I never really cared so much about any of these, I never cared so much about U. I'm always really calculating changes in U because stuff is happening. And I don't care so much when things aren't happening. Not that we don't study things at equilibrium, but I kind of am curious a little bit more before we get to equilibrium. So, I forgot why I'm talking about it. Anyway, all right, so forgot why I'm talking about that. The third law comes via the Nernst Theorem, so it always bothers me what we call a theorem, what we call a law, how I can actually prove the second law. I thought laws were things we can't prove, And now the third law is going to be proved via a theorem. Why isn't it the third theorem? Anyway, so this is called the Nernst. And I better learn N-E-R-N-S-T. Nernst Theorem. I may have gotten that right. Okay, so this guy was Walter Nernst, German, Jewish. He did not die at the hands of Hitler, but his career was cut short because Hitler removed a lot of Jewish scientists. So fortunately, that was the worst thing that happened to him. He actually almost invented the incandescent lamp. You know, Edison didn't invent the incandescent lamp, he perfected it. So it was actually something you'd want to buy. Just a heads up, so sometimes I do some consulting with companies, and one thing I've learned from them is that, like, some of the things, they're trying to make displays out of the materials I make in my lab, and one of the things I've learned from them is any commercial product has to be able to function in the on position for about 10,000 hours, or no. If something breaks too early, even if it's cheap, you're just not going to want it. So Edison basically perfected the light bulb, but Nernst is the guy who started building them. He also, now this is awesome, he built the world's first electric piano. That's where you get the electric guitar, by the way, which was invented by Jimi Hendrix. None of you, no, it wasn't, by the way, it was Les Paul, I think. I think it was Les Paul, but anyway, whatever. Okay. Child of the 70s, all right? So, okay, so electric piano. Now, what he said was the entropy, so I'm going to use some shorthand, entropy of a perfect crystal at 0K is 0 joules per K. Okay, so that's the Nernst theorem, which is also simultaneously the third law. For some reason, a law is also a theorem, but what do I know? Okay, so what? So again, what's kind of cool is it's still about, I find it kind of remarkable that laws 2 and 3 are about entropy, yet if law 2 says that entropy is why things happen, well, heck, that certainly sounds like really important. It's why you're here. Okay, now what this means practically is, so this is kind of neat. This is kind of neat how this works. What we're going to do is assume that we know entropy at some starting point, and then we tack on changes of entropy. So let's say that we know entropy, and we're going to say that's at 0K. Okay, so reactions are not particularly useful to be performed at 0 degrees K. So what we then do is tack on the changes of entropy. Now I'm doing this for a chemical, by the way. This chemical B or A or whatever. These are real things. Now before, this is why we have such a break with this material, is that before it's always been a magic cylinder with a perfect gas or a van der Waals gas. Not that those aren't still real things, but for the most part they've been kind of nebulous, right? I didn't really have to say what. Since it's a perfect gas, it doesn't matter whether it's oxygen or nitrogen, but anyway. Okay, so this is going to be applicable to a chemical, and no two chemicals will be the same. So again, if I know the entropy at some starting point, what I'm going to do is tack on changes of entropy, and what I'm going to do is warm it up, because this isn't the planet Pluto, and things are a lot warmer than 0K. Okay, so now you know, I'm going to follow my notes here. Okay, so the first thing I'm going to do, all right, is here at 0K, everything's a solid. So let's heat it up. And you know that, based on what I talked about earlier, okay, so remember, hopefully you remember that heat is Cp dt, and of course over temperature, and this needs to be reversible. I'm leaving that out, I kind of ran out of room. Anyway, so Cp dt over T, there we go. And we're going to start at basically 0K. And now I'm going to start, and let me get rid of this. I hope you do recognize that that is heat over temperature, and that is what entropy is. Reversibility, by the way, is we make these measurements in ultra good calorimeters. In fact, a guy got, his name was Joke, used to work, my PhD was performed in Joe Call, so he was the guy who made calorimeters that could go down to 0 degrees K and made it possible to make these measurements, so we got a Nobel Prize for it. He used magnets, by the way. You know, you can liquefy gases to get down to like 5K, but below that, you have to use magnets. So anyway, that's kind of, look it up if you're curious. It is neat. Okay, so entropy is 0K, and now we're tacking on changes. We're going to start it. I need units. Sorry. And then, if we're going to, let's do nitrogen. We're going to heat it up to the point where it melts. Now, this is some things you want to get used to. Melting is called fusion, F-U-S, fusion. That is the IUPAC, International Union of Pure and Applied Chemists. I think that's right. I'm pretty sure that's right. Have defined all the symbols and words for this stuff. So for some reason, fusion, which I normally think would be freezing, but it doesn't matter. So it's also melting at the same time. So we have a solid until it melts. So there you go. That's pretty simple. So then what? Okay, then, now this is where it gets kind of funky. This is the new thing. You haven't seen this before. But when things melt, their temperature doesn't increase. Right? Now, you input energy to make things melt. Just like, I don't know how much of a science geek you were in middle school, but if you put a cup of water, I have a demo today, by the way. If you put a cup of water in a freezer, it'll get to 0K, but it doesn't like turn to ice a second later. It's going to sit there maybe another half an hour till it forms, till it's ice. And that's because heat is still coming out of it, despite the fact that it's not changing its temperature. That's actually so that's because a phase change is occurring. And by the way, when you're looking for phase changes in exotic materials, there's all kinds of phase changes. I'm going to try to tell you about some of them, other than just ice melting, which is boring, obviously. You have phase changes in magnets, phase changes in biological membranes, like cell surfaces. Cell walls have phase changes. I find magnetic phases to be, I think that's really neat. So anyway, there's lots of phase changes, and you actually look for that behavior. You look for the ability to add heat, yet the temperature doesn't change, and that's how you know a phase change is occurring. So anyway, so you're adding heat, and what you would be doing is, of course, melting the solid, and that's the heat that you add, the fusion enthalpy. We're assuming we're at constant pressure, by the way, so that's why CP. Remember that you can't really heat this, just like I was saying before, you can't really heat a solid and keep it at constant volume. How would you do that? Maybe you could, but maybe it's just easier not to, right? Okay, and then of course we divide that. That's the heat over the temperature. All right, now, okay, at this point we're done. Let's, of course, we're doing a gas. I think I said nitrogen or whatever. Of course, now it's a liquid, and the liquid eventually vaporizes. It has a different heat capacity. The heat capacity varies with temperature, and I talked about that before, so I don't want to say too much more about that. And okay, so now it's now the liquid is at the boiling point, but it hasn't boiled yet, so we have to again just like how water can get to 100, but you don't see bubbles forming yet. You have to wait a little bit longer. Okay, now the IUPAC word for boiling is vaporization. That one, that's not hard. That one makes sense, but vape. Okay, most gases, especially nitrogen, I think we're at 63K at this point, so we still have a way to go to room temperature. And so, where are we at here? 1, 2, 3, 4, 1, 2, 3, 4. And hopefully I haven't forgot something. I feel like I'm forgetting something. And then we'll do, T is 298K, CP, PT. Okay, that's it. Now the next phase would be a plasma, so we're not too worried about that at room temperature. Okay, and then this will be the entropy at 298.
divide through by T?
Yes, thank you. Yeah. So CPLN T with a 63K for nitrogen and T98. Yeah, thanks for pointing that out. Remember that heat capacity is actually starkly temperature dependent. I'll show you that. I talked about that before. I'll show you how that's manifested through entropy. Okay, anyway, so other than introducing the enthalpy changes, the phase changes, which is hopefully not particularly difficult to understand, here's what the Nernst Theorem third law does for you. You see, the thing is, all of this is still a change in entropy unless I have a solid starting point. Then all of a sudden, magically, it's not. So because I know that the entropy at 0K is actually 0, this is no longer delta S. It was delta S, but now it magically becomes S. Not delta S, S. So that's why the third law is actually huge.
Why does it become S and not delta S with a different reference point?
What's that?
Why does it become S and not delta S with a different reference point?
Well, I mean, if your reference point is accurate, I mean, yeah, you could use a different reference point, but this is one that we know that we know. Yeah, I mean, it would, yeah, if you have a different reference point. Wait, what's it? Huh?
Never mind.
Yeah. So, anyway, it works. Right, question.
Would it be like if you were to subtract S 0K technically,
From the
it would be
other-
delta S equals that whole thing? That's
Right.
why it's like that?
Yeah, so that's why it'd be delta S. It's the thing is, if you don't know what this is, you would just subtract it from the left-hand side, making it all the delta S, and then all of these guys as well. This is new, but CPDT, this ends up being heat capacity LNTF over TI, which I have been telling you is delta S. But now it's not, and again, it's only because I actually know what I know what that point is. All right, question.
Is it always going to equal 0 joules over K, or does it?
Now there is a concept, are you referring to the concept of residual entropy?
Entropy at 0K.
Okay, so it turns out, well, maybe you've heard of this before. There's this thing, I actually don't cover it because I find it kind of a little silly. Anyway, not because any of this is silly, but it's thought that any chemical at 0K, and if it's been crystallized, the entropy is 0. And this is what people in the 50s, when they started tabulating, like when you do Hess's law, you look in the back of the book and there's a table with H's, delta H's, and delta G's, and entropies and CPs. You remember that? Those tables were filled out in the 1950s by people just getting everything they could get their paws on, hopefully purifying it, which is kind of hard for engineers, and that's where sometimes the mistakes were made. Freezing things down and then heating it back up again. And then they filled out those data tables, which was really crucial for the development of the chemical industry. Because you can, as you probably already know this as we're covering, you can predict reactions you actually haven't done yet with Hess's law calculations. Okay, now the reason I'm bringing that up is, if the crystal is perfect, now take the entropy of CO gas. I don't know what it is offhand, but it turns out that, of course, I want to have a crystal of CO gas all lined up. And I'm sure that there's more to the crystal structure than this. There's face-centered cubic and body-centered cubic, and molecules can do that. But regardless, did you see what I just did? Did you see what I just did? I put one of them in reverse. Okay, so it is known that when we want to practically build out these tables of data, that some measurements are a little flawed. And it's kind of things that are obvious, like CO, water. Water is one of them. And it turns out that the entropy at 0K is not quite 0. And that's called residual entropy. And I think you might have heard that. That's why you're asking that. So sometimes the entropy of some things is not 0 at 0K. It's a little, like way tiny. It's tiny, all right? It's tiny, but it's not exactly 0. And it's kind of important to get it exactly right. And it only comes up for some obvious, I mean, it's kind of obvious, right, that this could get flipped. Water can get flipped because it's not clear which protons belong to it, which is a tunneling thing, which is a quantum thing, which is a 346. I'll talk about it at 346. I tend not to bring it up. It's not even in my notes. It's not even in the book. I do need to add it to the book, but it's a bit of a glaring error because I consider it kind of just our inability to get that SOB right there to behave itself. I wouldn't be surprised if some engineer, figures out some way to kind of get things to stop doing this. It might help if we could make things colder. You can't ever get things truly to 0 K. You can only get arbitrarily close. So I have a feeling that if we build better refrigerators to get closer and closer, like the record is like 10 to the minus 6 K, right? 10 to the minus 6 K or something like that. So maybe we'll get 10 to the minus 9. Maybe that guy will flip back and then we'll get an accurate measurement. So anyway, we're going to presume that it's 0 K. It's not necessarily true. Again, that's called residual entropy. I'm not going to bring it up again. I have to admit, I'm really curious how anyone knows that, though, because we were making these measurements in the 50s, and it's like 1 out of a million will get out of line. 1 out of a million get out of line. I don't know how they knew that. So, any other questions? So, yeah, because this really is kind of brainlessly easy, a little stupid in my opinion. I kind of almost hate covering this stuff, but, okay, let me show you a little bit what a graph of what this looks like. Now, I have a graph in the book. I'm going to show you I'm going to draw something that's a little simplified. In the book, that took me really a day to get that data, by the way. I do show the entropy calculation for nitrogen, so that's real data. And I had to admit, I had never actually done this, but when I got the data from like really old engineering papers, I got like the temperature dependent heat capacities, and I actually did this calculation. I actually did get the same entropy as I found in data tables in the back of the book. Other people's books, not mine, but so this does work. What was kind of interesting though is that there's actually 2 solid phases, so it undergoes a phase transition while still being a solid, and we're going to cover some of that a little bit later. So you end up with twice as many terms for the solid than you would expect. Anyway, so I'm going to simplify this. I'm going to say that there's just 1 solid phase and point out that this is how this stuff looks because there's actually this little nuance. Okay, so this is in joules per K, and we're going to start at 0, 0. This will be, of course, in Kelvin. You can just assume that. In grad school, if a grad student at their qualifier exam doesn't put units or doesn't label their graphs, we scream at them. It's like the big faux pas. Okay, neat thing is, I'm going to tell you a little bit more about this. At low temperature, solids entropy rise, and heat capacities is the same thing, rises TQ. Don't write that down. We're actually going to cover this in 346. And I want to preview a little bit of 346 stuff here. So I'm going to tell you a little bit about why this is. But you don't need to write it down. It's kind of this historical, it's actually how people discovered quantum mechanics, by the way. So I want to tell you a little bit about it because it's kind of neat. Okay, now this is the fusion temperature. Okay, now what happens is that the melting gives you just a solid jump, but remember it's at the same temperature. And then what you get are rather simple monotonic rises, which just means monotonic, by the way, it means just it goes up. Then of course we get to the vaporization, and then it just jumps up again. And I'm probably not doing this to scale. And it still rises, but it doesn't rise as much. The slope isn't as big. And that's because we're dividing heat capacity by temperature, and the temperature is getting really big now, like, 200, 250 K, right, almost room temperature. So it looks this way. Anyway, and I showed this again in the book, although there's 2 solid phases. I didn't want to, I like using real data. Some of those graphs took me like a day or 2 to make because I wanted to get real data. Okay, now I want to tell you a little bit about why is this, that's proportional, by the way. Why is entropy increased proportional to T cubed? I'm going to explain why. Question?
Yeah, going back a little bit, we have our S equation. Why is it equal to delta H over T? Is that just something that's known?
No, that's heat. No. This is still, it's still technically, given our starting point, when you add the changes, you still have the absolute entropy. Again, not that that's a big deal, but it's just kind of neat that it does work that way. That's heat over temperature. remember I said yesterday, we're at constant pressure and temperature from now on. I'll go back changing temperature, sorry about that, but anyway. Also, when you make this measurement, everything's a solid, and we're not gonna have CV, because you can't really keep things practically at a constant volume when you're heating them. And when it comes to inputting energy to melt something, enthalpy is the heat. And so this is still heat over temperature. And the calorimeter tells you how much heat you add. You can actually track, when you have a calorimeter, it actually spits out heat capacity, and what you'll see is that it'll actually go crazy because you're inputting heat, but the temperature's not changing. So you see the heat capacity go nutty on you. That's how you know you have a phase transition. And when that stops, you know that the phase transition stopped, and so then you know how much heat you added to the substance.
So just delta H is equal to delta Q?
Yes, as long as we're at constant pressure. Relatively easy measurement to make. Question?
So that third term in the equation, the one before it, that one, yeah. That on the graph, that's represented by the vertical line, right?
Yep.
Cool.
Yeah, just a sudden increase in entropy, but at the same temperature. Phase transitions are at constant temperature. Okay. Let me tell you about this, though. This is how we discovered quantum mechanics. Back in the 1930s, people got obsessed with how heat capacity and thus entropy of solids rises as T cubed. They absolutely went bonkers over this. You may recall, if you look at the graphs in the book, the graphs of heat capacity and entropy aren't terribly different. The heat capacity is like the running sum. Sorry, entropy is basically a running sum of heat capacity via this equation. Okay, but they got obsessed. Why does entropy of heat capacity, why does it rise as T cubed? And you think like, well, who cares? But they got obsessed over it. Einstein weighed in and he couldn't answer it. Einstein never believed in quantum mechanics. I'll mention that a couple of times in 346. We don't talk about Einstein much in 346, and he didn't believe in quantum mechanics. 346 is really all about quantum mechanics. Debye figured it out, and then just like a year after Debye figured out why this works, then Schrödinger and Heisenberg came up with quantum mechanics. Here's what's going on. You got to think about a solid. So it's a solid, right? Of course it's a solid. So we have solid. Now I'll draw a lattice in the most simple manner possible. And you're inputting heat, and the temperature is rising via the heat capacity. What Debye was trying to figure out is why does the heat capacity basically, and thus entropy, rise as T cubed? The answer is, what does it do with that energy? It has to have degrees of freedom, and you know that what it's doing, these atoms are doing with that energy is they're moving, right? You know that, right? So, right, they're moving because what else can they do? Here's what Debye figured out. Now, you've heard of quantum mechanics called wave mechanics before. Let me show you a wave. Imagine that this atom, all right, so this is the solid. So these are the atoms, so it's like in a vice, okay? Now imagine that these atoms are vibrating. And so they could do like this. Sorry, not so much. Like that. It's a wave. Low frequency, high frequency. What do you think? Low frequency. Right, that's low frequency. Low energy or high energy? Low energy. Low frequency is low energy. I don't you know that, right? Like if you have a person who can sing with a very high voice, they shout in the glass, right? Your gut sometimes tells you the right thing. Sometimes, not always, but sometimes. Okay, now here's where Debye figured out that these things moved in waves. As I mentioned, wave mechanics, but now let's talk about there's a cutoff. There's a cutoff to these frequencies, and that's where you get the T to the 3. I'll actually cover more of that next time. But now let's do a high frequency. Let's do a high frequency. Okay, up, down, up, down. Okay, so your wave is like this. The wave has a wavelength of basically 2 bond lengths. Okay, high frequency, high energy,
Yeah.
right? Can you have a higher frequency wave?
Yes.
Okay, tell you what, let me redraw. So a lot of you said yes. Okay, I'll redraw how the atoms are moving, and I'll double the frequency of this wave.
No, it's quantized.
More accurately, this just isn't real. This just isn't real. You see that? Yeah, so you see how this wave is a good description of this. Yet it's the same as this wave. Right? This wave describes this atom up, that one down, that one up. This wave does that with times the frequency of this one. So what's real and what's not? Right? Now, how can you say that this is happening when you have no ability to tell? There's no atoms in between. So I contend this isn't real. Not when this is that's real. I don't know how else to put that. So what Debye figured out is that there's a limit to the frequencies that these things can vibrate at, and that frequency is dictated by the bond lengths. Again, the wavelength is twice the bond length. You see here, 1 bond length, 2 bond lengths, and there's your wavelength, right? I get a little confused by sine and cosine, but anyway. Okay, now because of atoms moving in waves, that's part of quantum mechanics, and that there's discrete numbers of waves, and that the number of waves that you could actually run out of them gives you this rise that is proportional to t cubed. And by the way, the cube ultimately comes from the fact that we live in 3 dimensions. We're actually going to do that calculation at the start of 346, but I couldn't help but talk about it because it's kind of neat, because they got obsessed, Einstein couldn't do it, Debye figured all this picture out, and Schrodinger and Heisenberg are thinking about waves, and they came up with quantum mechanics. That's historically how all this went down. So I just thought that was kind of neat. You don't have to remember any of that, but I just wanted to point that out because, again, it's kind of cool. Anyway, so I have a little bit of time left. I want to point out, so, when it comes to Hess's law questions, some of products minus some of reactants, I'm not going to cover that so much. I'm going to show some weird examples because, again, you folks did do this in you did it in freshman chem, right? For delta G of products, myself. You've done this, so I'm not going to spend a lot of time on that. It is kind of freshman-ish or high school-ish. So I want to point out that you get chemicals. I'm going to occasionally, you know how to do that, but occasionally I'm going to trick you into making mistakes, and that's going to make you, that's kind of more what I'm going to do. Makes you appreciate how this stuff works. Okay, when you look at a table in the back of the book, this is what you see, and I'll leave out, these are usually joules per mole, and then let me ask you this. How am I doing? I got about 5 minutes. I can cover a little bit of this. Okay, you got entropy per mole. Okay, you got this little symbol here, and I won't write this, well, here, I will. This means 25 degrees C and 1 bar pressure. So this measurement, well, I just erased it, but the entropy thing was calculated to a final temperature of 298.15 and constant pressure that it was held, whatever it is, was held in the calorimeter under an atmosphere of 1 bar. So there you go. So that's what the little circle means. If we change temperature, we won't be able to use that little circle. And we're going to change temperature a couple of times. And that's also on your homework. There's example questions in the book on how to do some of the harder questions on your homework, by the way. So look there if you get confused. Okay, again, you've seen this before, but now I want to ask you this. Now, of course, everything's per mole. Do you see this? Do you see this in the book? Or do you see this in the book? Which one? Do you see H or G? Or do you see delta H or delta G? You see deltas. You don't see a delta in entropy, but you see deltas in G. Why is that a delta in G? Why not absolute G? Now remember, and of course, N2, number, anyway. G is U minus plus PV, minus TS. That's G, not delta G. Why is there a delta G and not a G? I know it's like, well, who cares? But it's kind of horribly important. Remember, I beat up on a lot of you on the first test when I had a Legendre transform, and a lot of you were writing change in the function and not the function. That just got wiped out. Change versus function, those are not the same. Think about entropy. How different is delta S versus KLNW, right? Those are hideously different. Why do I have delta G and not G? Any opinion?
It's hard to calculate an absolute value for you.
Yeah. Wait, you read the book.
No.
Yeah, so that, it does come down to that. It does come down to that. That entropy, for the reasons I've just been talking about the whole time, can be measured with certainty because we have a third law for it. But the damnedest thing is, now pressure volume, I know what that is for a gas. Temperature, I know what that is. The entropy, I know what that is. But that is actually a problem. Now I have you kind of think maybe I have you by the equipartition theorem, 1/2 RT degrees of freedom. It turns out that is the U, oh, remember when we talked about this? That's the U only for translation, rotation, and vibrations. That's all that U is for. That allows us to calculate pressure, temperature for gases expanding and contracting, which is how motor cars and power plants work. That's really quite useful. However, it was actually completely inaccurate. Now the problem is, when A reacts with B to form C, the problem is that there is no chemical reaction, except, well, technically isomerizations. Technically melting is a chemical reaction. It's very boring. Isomerizations are chemical reactions. Melting is a chemical reaction. I will do some chemical reactions of melting at times, but for the most part, when something real happens, electrons are changing place. Take combustion. If something combusts, it gets oxidized. What does that mean for the electrons? Goes up or down? Down, right. Oxidation means you lost electrons. Oxygen is an electron thief. There's also oxidation reactions that don't necessarily involve oxygen. We have multiple words. We have one word that means multiple things, unfortunately. Oxidation is one of them. We're losing or gaining electrons. Combustion, you lose electrons. Reduction, you gain electrons. Anyway, U, via the equipartition theorem, was not designed to handle electrons coming and going. It wasn't designed for that, so it doesn't include that. So degrees of freedoms of electrons, I don't really even know what that is because electrons are quantum mechanical. So when I gave you the formula for U via the equipartition theorem, it was only if that gas was not, that was the energy of that gas, but that gas was not allowed to go through a chemical reaction. If so, I'm kind of using the wrong number. I had to use a different equation. It gets worse. Actually, you can use supercomputers now to calculate U of chemicals. You use these really advanced quantum mechanical software, and it can actually tell you what U is, but we've only been able to do this really in the last 5 or 6 years. So, no absolutes. These tables are not absolutes, they're deltas. So what happens is, it turns out that energy is relative. And if you can just basically define some standard energy, then chemical reactions can be defined as being plus or minus relative to that standard. And it will always work. If you make a measurement of the reaction compared to that standard, it'll always work out exactly, your calorimeter will spit out the same result. So that's why we have deltas in here. And next time, I'm going to explain what the standard is. The question.
What does that say?
What's that? It's defined. It's defined